In this chapter, we are going to discuss simple linear regression. My videos on simple linear regression will deviate from the textbook a little bit in order to provide a coverage of this topic in more depth and more details. To introduce linear regression analysis, let's take a look at an introductory example first. Consider the relationship between sales for a company and the amount of money it spends on advertising. It is generally expected that sales depend, at least to some degree, on the amount of money the company spends on advertising. Of course, many other factors may also affect the sales, such as the competition the company faces, the product quality, after-sales services, etc. But we're still interested in understanding the relationship between sales and advertising, and how advertising investment would affect sales. Regression analysis is such a tool to analyze the relationship between sales and advertising and help us predict average level of sales given the level of advertising investment. We start regression analysis with data collection. Suppose we have the following data of 10 observations. The number of observations in regression analysis is called sample size. For example, in two instances of investing $40,000 in advertising, the resulting sales are $279,100 and $244,000 respectively. In regression analysis, a preliminary step is to plot scatter. Scatter plot gives us a qualitative sense of the relationship between sales and advertising. It is quite clear that, in general, the more advertising there is, the more sales are. In addition, it appears that there exists a linear relationship between the sales and advertising. It is worth noting that the linear relationship between the sales and advertising we observed in scatter plot is not perfect. As we mentioned on the previous slide, given the same level of advertising, say $70,000, there are possibly different levels of sales. Next, we're going to introduce functional relation and statistical relation. In mathematics, we're already familiar with functional relation. Following our example, we call the actual sales Y and the advertising investment X. If sales Y and advertising X followed a functional relation, in general, it could be written as Y is equal to f of x. To keep it simple, let's say sales Y and advertising X follows a linear functional relation given by Y equals 0 plus 60x. If the advertising is $40,000, then the sales must be $240,000 exactly. Clearly, the relation between the sales Y and advertising X is not a functional one. Instead, it is a statistical one. A statistical relation between Y and X can be written as Y equals f of x plus epsilon, where epsilon is a random variable referred to as the error term. In our example, epsilon is the change in sales that cannot be explained by the linear relationship between x and y. It might be due to other factors such as competition, economic conditions, among others. The equation that describes how y is related to x, an error term, is called the regression model. In our example, we're actually dealing with a special case of regression model, a simple linear regression model. In this case, yi is equal to beta 0 plus beta 1 times x1i plus epsilon I. Here, yi is the actual sales for the ith observation. Generally, in regression analysis, yi is called dependent variable or response variable. X1i is the advertising for the ith observation. Generally, in regression analysis, X1i is called independent variable, or explanatory variable, or predictor variable. In machine learning, it is also called a feature. In simple linear regression, there's only one predictor or independent variable, so for convenience, we often ignore the subscript 1 and simply write xi. In multiple regression with k predictor variables, we'll then have x1i all the way to xki. Epsilon I is the error term for the ith observation. Because epsilon I is a random variable, yi is also a random variable. Beta 0, beta 1 are called population parameters or regression coefficients. As you can probably tell, the subscript I indicates the ith observation. In our sales versus advertising example, the total sample size is 10, so the value of I will go from 1 to 10. More often than not, we may drop the subscript I for the sake of simplicity and convenience. Conceptually, we are assuming a large population of Y values or sales values in our example occurs at each level of x1, the dollar amount spent on advertising. The parameters beta 0 and beta 1 represent the intercept and the slope of the true regression line with respect to those populations. That is why beta 0, beta 1 are sometimes called population parameters. Usually, even though the exact numeric values for the population parameters exist, we typically don't know what they are because it is practically impossible to look at the entire population in most cases. Instead, we can take a sample of Y values at selected levels of x1 and estimate the values of the population parameters. Now it's time to discuss the key assumptions of regression analysis. Simply put, these assumptions can be summarized into one sentence. All epsilon i's are independently and identically distributed following a normal distribution with mean 0 and variance sigma squared. First, the expected value of epsilon I is 0. As a result, the expected value of yi is equal to beta 0 plus beta 1 times xi. This is called simple linear regression equation. Second, the variances of all epsilon i's are equal, denoted by sigma square. As a result, the variance of yi is also sigma square. This is true because beta 0 plus beta 1 times xi is a constant. Third, the error terms are independent of each other. This implies that the covariance between epsilon I and epsilon j is 0. Lastly, every error term is normally distributed. In simple linear regression equation, E of yi equals beta 0 plus beta 1 times xi. Beta 0 is the y-intercept of the regression line, beta 1 is the slope, and E of yi is the mean or expected value of y for a given value of x. Sometimes, a value of the response variable y is called a response. As a result, E of y is sometimes called mean response. As mentioned earlier, it is almost impossible to know the exact or actual values for the population parameters beta 0 and beta 1. By taking a sample from the population, we can estimate the values of the population parameters. These estimates, often called sample statistics, are denoted as B0 and B1. We then have the estimated simple linear regression equation. yi hat equals B0 plus B1 times xi. Just to remind you here again, In simple linear regression, there's only one independent variable. As a result, it is convenient to simply use xi instead of x1i. We'll use them interchangeably. Arguably, the most popular way to estimate regression equation is the least squares method. The criterion used in least squares methods is the sum of the n squared deviations, which is given by this formula over here. For convenience, we call the sum of the n squared deviations q. Here, n is called sample size, which is the number of observations in the given sample. In our example, sample size n is equal to 10. Since q is some sort of deviation, it is natural that we want to minimize it, and b0 and b1 are just the estimators of beta 0 and beta 1 that minimize q for the given sample observations. Here on this slide, we provide the formulas for computing b0 and b1, the estimators of beta 0 and beta 1 that minimize q for the given sample observations. If you understand some calculus, it is actually rather easy to derive those formulas. We simply take first-order partial derivatives of q with respect to beta 0 and beta 1, then replace beta 0 and beta 1 with b0 and b1 in both partials, setting the two partials equal to 0. Solving for beta 0 and beta 1 will yield the two formulas you see here. We'll discuss the mathematical part of regression analysis in a separate video. In the formulas, x bar is the mean of the independent variable, and y bar is the mean of the dependent variable. Based on the estimated regression equation, we can easily compute the predicted value of y for any given x. This value is also called fitted value, denoted as yi hat. Here, we introduce another very important concept in regression analysis, the error or the residual. The residual is denoted as ei, which is simply the difference between the actual y value and the fitted value. We'll have lengthy and in-depth discussion on the residuals later. Without getting into too much mathematics, we present some key properties of least square estimators. First, note that b0 and b1 are also random variables because their values are for sure different for different set of sample observations. The expected value of b0 is beta, and the expected value of b1 is beta 1. That is to say, b0 and beta 1 are unbiased estimators of beta 0 and beta 1 respectively. This is part of something called the Gauss-Markov theorem. Second, b1 is a linear combinator of yi. That is to say, b1 can be written as k1 times y1 plus k2 times y2 plus all the way to kn times yn, where k1 through kn are constants. This is an important property because this property makes it possible for us to find standard error of b1 and many other important values. Lastly, Gauss-Markov theorem also says that b0 and b1 have minimum variance among all unbiased linear estimators. Let's take a look at our sales versus advertising example and see how we can apply the formulas to find the values for b0 and b1. I did all the calculation in Excel. Here's a screenshot of the final results. In cell B14 and C14, we compute the mean advertising and mean sales, or simply x bar and y bar. Based on those two values, we compute xi minus x bar in E column and square of xi minus x bar in F column, y minus y bar in G column, and finally xi minus x bar times yi minus y bar in H column. we take the sum in row 14. In the end, B1 is simply equal to the value in H14 divided by the value in cell F14. Once we find the value for B1, it is easy to compute B0. In our example, B1 is equal to 5.55 and B0 is equal to 36.34. That is to say, for every additional $1,000 investment in advertising, we expect that the sales will increase by approximately $5,550 on average. It is worth noting the limit of our simple linear regression model. In our example, the values of x range from 30 to 90. It is not advised that you predict sales for values of advertising less than 30,000 or more than 90,000. Of course, nowadays, such calculations have already been automated. Many software can compute B0 and B1 and do much more with just a few clicks of your mouse. Actually, Excel itself has a regression tool in its data analysis add-in. Now, we look at the least square estimators from another perspective. First, let's normalize or standardize all the values of x and y by computing their respective z-score. In our dataset, we can replace xi with its corresponding z-score, z sub xi. Similarly, replace yi with z sub yi. It is obvious that the mean value of all zx is 0 and the mean of all zy is also 0. It is also straightforward to show that the variances of zx and zy are both equal to 1. As a result, the standard deviation of zx and zy are 1 as well. Now consider the sample covariance between x and y. We write the definition of covariance in terms of zx and zy. We have s sub xy equals the sum of zx times zy divided by n-1 times sx times sy. Similarly, we write the Pearson correlation coefficient between x and y in terms of zx and zy as well. And we have the correlation coefficient r equal to sum of zx times zy divided by n-1. With what we have on the previous slide, we can write B1 in terms of zx and zy, and B1 is equal to sum of zx times zy divided by the sum of zx squared. We can simplify the formula for B1 even further. It is simply r times sy divided by sx. With simplifying the formula, we can easily tell that over 1 standard deviation in x will predict r standard deviation up in y. Now, let's consider the normalized data set with x replaced by zx and y replaced by zy. If we run regression with zx against zy, the resulting estimated regression function is zy hat equals correlation coefficient r times zx. This means for every standard deviation we deviate from the mean in x, we predict that y will be r standard deviations away from the mean in y. You should be able to prove all the results mathematically with some simple algebraic manipulation. Next, we'll demonstrate the result zy hat equals r times zx numerically with our sales versus advertising example. Based on the original data on x, advertising, and y sales, we compute the mean, standard deviation, covariance, and correlation coefficient r. Pearson correlation coefficient r between x and y is simply equal to covariance between x and y divided by the product of standard deviations of x and y, which are denoted as sx and sy. In this case, r is equal to 0.9844. Recall that B1 is also equal to r times sy divided by sx, we can compute the value for B1, which is 5.550, identical to what we had a few slides ago. Now look at the right part of the table. In the fourth and fifth columns, we normalize the data resulting in zx and zy. In the sixth and seventh column, we compute zx times zy and zx squared. At the bottom, we calculate the sums. With that, if we run regression with zy against zx, the resulting slope is 0.9844, which is nothing but the Pearson correlation coefficient between x and y. There's one more thing I'd like to mention before we move on, r squared. Since r is 0.9844, r squared is just 0.9691. The latter is also called coefficient of determination in regression analysis. In simple linear regression analysis with just one predictive variable, we have coefficient of determination equal to the square of correlation coefficient. This will not be true in multiple regression analysis. Next, we will formally introduce coefficient of determination.